All right, hi there. So yesterday you kind of reviewed polynomial functions a little bit on your own with Desmos, and today we're going to go over some more formal review there. So just a couple of reminders of some of the key concepts and words we're going to be using. When we say term, right, we're talking about a number variable or a number and variable combination. A degree is the exponent of any variable. A polynomial, when we say polynomial, that is a monomial or the sum of monomials. So a term could also be thought of as a monomial just all on its own, whatever its coefficient variable combination is. Now when we say polynomial degree, that is the largest degree of any term in the polynomial. So the polynomial degree is the largest exponent you'll see. And then finally, standard form for polynomial functions will arrange it basically in order from largest exponent to smallest exponent. And there are a couple of other terms we can use to describe polynomials. Some of them are based on the degree, right? The highest exponent you see. Some of them are based on the number of terms that you have, whether you have 1, 2, 3, or more terms. So just some vocabulary to remind ourselves there. And then the first thing we're really going to talk about in detail is this end behavior. And remember that the end behavior refers to the direction of the graph on the far left. So that's as x goes to positive infinity. And on the far right, oops, I got those backwards. Far left is when x goes to negative infinity. Far right is when x goes to positive infinity. So let's take a look at that. So if our degree, I should also add that leading coefficient is the coefficient of the term with the highest degree. So once we know the highest degree, knowing the coefficient that goes with it is also going to be helpful when we're talking about end behavior. So our polynomials can either be even or odd. They either have a large degree that's an even number or a large degree that's an odd number. So if it is an even degree with a positive leading coefficient, so something like 3x to the fourth plus 2x squared minus 9, that has a highest degree of 4, so it's even, and its leading coefficient is positive there. This graph might look something like this, but the key here is that when we have an even degree, the ends are always going to go in the same direction. If we have a negative degree, a negative leading coefficient, so something like negative 2x to the sixth minus 3x squared. Again, we have an even leading coefficient, an even degree but a negative leading coefficient. That graph will open downwards. And one way to kind of keep this in mind is that if it's an even degree, the end behavior is going to be the same on both sides. So either the y values will both approach infinity or they will both approach negative infinity. So even, balanced, same on both sides. Whereas if we have an odd degree, then our ends are going to go in different directions. So for instance, a positive leading coefficient, something like 3x to the third minus x squared plus 7. We have an odd degree, but a positive leading coefficient. This graph might look something like this. On the left-hand side, or as x goes to negative infinity, y is also approaching negative infinity. As x approaches infinity on the right-hand side, y is also approaching infinity. It is going up forever. But if we have a negative leading coefficient, then our graph will, our end behavior will be reversed. This time as x goes to the far left to negative infinity, y approaches really large positive values, infinity. And as x goes to infinity on the right-hand side, y will approach negative infinity. So just something to keep in mind here about we're using a combination of the degree and the leading coefficient. So I'm going to have you check out these two examples here about the end behavior of these graphs. Oops, got a little ahead of myself there. So as x approaches negative infinity and positive infinity, well, we have an even degree with a positive leading coefficient. So this is going to be going up and up on both sides. So y will be approaching infinity on both sides. Whereas example B, we have an odd leading coefficient, or excuse me, an odd degree. So our end behavior is going to go in opposite directions, and our leading coefficient is negative there. So as x approaches negative infinity, y actually approaches positive infinity, and as x approaches positive infinity, y approaches negative infinity. So it takes a little bit of practice, but you have these notes here to use as resources. So the end behavior is not the only important part of polynomials. Say that 10 times fast. But we also want to know about what's going on in between. So if I have a polynomial, right, we've got an example, p of x right here, then the statement x minus b, if we consider that a factor of the polynomial, then that means that that value b is a 0, it is a solution, it is an x-intercept. Remember, all of those are really kind of the same idea. They're just different terms depending on the context you're using. But zeros, solutions, x-intercepts, even roots, right, is another term that we used. So when we're talking about end behavior and the things in between, x-intercepts are really valuable bits of information. So thinking about how do we use this? Well, I've got three factors of this polynomial. I've got x minus 1, I've got x plus 1, x minus 1, and x plus 3. So to find the zeros, I'm going to set each one of those individually equal to 0. So if x plus 1 is equal to 0, that means that x must be negative 1. If x minus 1 is equal to 0, that means that x must be positive 1. And if x plus 3 is equal to 0, that must mean that x is negative 3. So we can find the zeros, but now we want to use those to sketch a graph of the function. So I'm going to make a note of those values. I'm going to do a little estimation here, but I've got negative 1, I've got 1, and I've got 3. Whoops, excuse me, that should be negative 3. Fix that right up. Negative 3. So I have those x-intercepts, but I can also think about my end behavior to help me kind of place everything in the right spot. So when I think about the degree and the leading coefficient here, I'm actually really asking myself, what's going on when I multiply, if I were to multiply all of this together, then that x times x times x would give me my highest degree. 1x times 1x times 1x would give me 1x cubed, which is odd with a positive leading coefficient. So my end behavior will be going down on the left-hand side as x goes to negative infinity and up on the right-hand side, if I were to go back and check my table of information, it would match with the odd degree and positive leading coefficient. And then in between here, if these are the intercepts, then I know that it's going to be kind of crossing through those to fill in that shape there. It certainly takes a little bit of, it's like a little logic puzzle to kind of fill in those blanks using all of our information. We can also use information about zeros to write a polynomial. So if we have these 4 zeros here, 2, -3, 5, and 0, we would write our polynomial by converting each of those into factors. So that 2, it would be an x minus 2 would be its factor. -3 would be x minus -3, or x plus 3 if I wanted to simplify that, which I should. X minus 5, and then that 0, if we have x minus 0, well, we could just simplify that to x. So now we've got all the factors that go along with our individual zeros. And so I can string this all together as a polynomial in factored form. I'm going to put that x out in front. That's just good convention there. Everything else I'll pop into place as a factor. Now, if I was feeling really adventurous today, I had a lot of extra time on my hands, which you might, I don't know, no judgment. I could multiply this through and get a degree 4 polynomial in standard form, but this works too. So the last thing I want to review is multiplicity. And so this means this is when the graph doesn't actually cross through the x-axis, it might simply touch. So a multiple zero, some people call it a multiple zero or a multiple x-intercept, is the resulting zero of a factor that occurs more than once. And we'll look at some examples of what that means. Multiplicity is the number of times the zero occurs, so aka the number of time that the factor occurs. So if a zero has an odd multiplicity, so it occurs an odd number of times, then that graph will actually just cross through the x-axis, like the example we saw up above. Whereas if it has an even multiplicity, then the graph will just touch the x-axis right there. Oops, sorry, scrolling around a lot. So I want to look at just an example to see kind of what this would look like and kind of put it all together. So we have this polynomial f of x, and it tells us that we have x squared times x minus 3 squared times x plus 5. And so it says, what are these zeros and what are their multiplicities? So the first thing I'm going to do is I'm going to identify those zeros, again, by setting each of these factors equal to 0. So x equals 0. Well, okay, x is equal to 0. X minus 3 equal to 0. That means that x is equal to positive 3. And if x plus 5 is set equal to 0, then x is equal to negative 5 there. So I've got my zeros. That's great. Now I want to know what the multiplicity is. And that's where these little exponents come in. So if I were to think about what it means to square something, that means multiply it by itself. So I could really expand this out to represent that actual squaring. And what I observe after that is that some of my factors occur more than once. Instead of x or just x squared, I have x times x. I have that factor occurring twice. I have x minus 3 occurring twice, and x plus 5 occurs once. So I can use the exponent to quickly identify my multiplicity. So if if I have x squared, then that 0, x equals 0, has a multiplicity of 2. x equals 3 also has a multiplicity of 2 because its factor x minus 3 appeared twice. X equals -5 has a multiplicity of 1, even though it doesn't have an exponent, right? It appears one time. It has a ninja exponent of 1, so we still count it as having a multiplicity of 1. And if we consider what this means, I do think we should make a sketch of a graph using this information. But those zeros that have an odd multiplicity, which in this case is just x equals -1, then we'll cross through the graph at that point. These other two zeros, the graph will simply touch there at x equals 0 and x equals 3. And I think we probably need to look at an example of how this will actually look in the end. So I'm going to try to do a better job of identifying my zeros this time. Okay, so I've got x equals 0, I've got x equals 3, and we'll put x equals 5 there. -5. I put it in the right spot, but I didn't call it the right thing. X equals -5. So if I want to make a graph and kind of think about what this means, something else I should think about is the end behavior. Right? So since we have, with this expanded form, we have 5 x's in there, that will be an odd degree, and it will have a positive leading coefficient because there's nothing in there, the x times x times x times x times x, that will give us a negative. So, if it's an odd degree with a positive leading coefficient, right, we're going to go down and then as x goes to -infinity and up as x goes to positive infinity. So I can kind of put those guides there and what that will mean. And then thinking about what's going to happen. So I will cross at x equals -5. So suddenly I'll be above the x-axis. And then once I come back down, at x equals 0, it says it will touch. So it'll just kind of bounce off the graph right there. And it'll do the same thing at x equals 3. And then it will go upwards, which is exactly what I wanted with that end behavior. So like I said earlier, there's a little bit of it's kind of a sense of a logic puzzle here where you're given lots of pieces of information. What's the end behavior? What are the zeros? How does it behave at those zeros? That you're then asked to piece together to a cohesive picture here. So these 3 practice questions, really you're doing exactly what we just did in that last example. You're not only identifying the zeros, but you're also using information about the multiplicity, right, and the end behavior to sketch a graph. So you can check your answers here. I hope you're doing well. Thank you for checking in and staying engaged. And take care of yourself and let me know if you need anything.